All right, so we're going to look at another proof by induction for products this time. So prove using mathematical induction that the product of 1 plus I 1 on I from I equals 1 to n equals n plus 1. So just a note on notation if you haven't seen this before, just like we use the capital Greek letter sigma to represent the sum, we use the capital Greek letter pi to represent the product of infinite terms. So let me show you what I mean by that. If we were to expand this out, what this sort of is shorthand for saying is, all right, it's going to be 1 plus 1 on 1, where I is 1 in the first case, then multiply by 1 plus 1 on 2, multiply by 1 plus 1 on 3, and so on, all the way up to 1 plus 1 on n. And what we're saying is that that equals n plus 1. And our job is to prove that using mathematical induction. And so the first thing we might want to do is outline the proposition, P of n for natural numbers n. Remember, that's always our first step with proof by induction. So what that's going to look like is basically just the problem to begin with. So let P of n be the proposition that the product of 1 plus 1 on I from I equals 1 to n equals n plus 1. And then remember what we need to do is need to show that the base case is true. And then we need to show that for some natural number k, that implies k plus 1, which just means you can get from some term to the next term, and then you've done your proof by induction. So let's show that p of 1 is true. So when basically we're going to look at the left-hand side, and when I is 1, or when n is 1, we should say, we'd just be evaluating this first term because we're only going up to I being 1 and also n being 1, which is doing the first term. So it can be 1 plus 1 on 1, which I think you would agree is 2. And similarly, we do the same thing on the right-hand side. N is 1, 1 plus 1 is 2. Doesn't get any easier than that in some sense. So what we want to do next is we obviously want to say that the left-hand side equals the right-hand side for the base case, and so the base case is true. So we've done sort of the first part. Okay, then the next step is always to assume that P of k is true for some natural number k. So that's going to look like this. Basically, we take the proposition and wherever we had an n, we just put in a k. So now we're saying, all right, it's true for some natural number k. So that's just going to look like this. And then we need to show that this implies that the proposition P of k plus 1 is true. So let's do that. Remember, what we need to do here is we need to sort of, again, look at the left-hand side and the right-hand side. So yeah, we're saying the product from I equals 1 to k plus 1 now of 1 plus 1 on k plus 1. So we sort of look at this, but replace all the k's with k plus 1s. We get this line here. On the right-hand side, we get k plus 1 plus 1. Okay, so let's just look at the left-hand side and see if we can sort of simplify that. We're going all the way up to k plus 1 now. So what that means is we're going to go up to k. We're going to take that sum, and then we're just going to multiply by the k plus 1th term, which would be 1 plus 1 on k plus 1. So just to sort of show what I've done here, we've taken the product of all those terms up to k, which is just this notation here, and then you multiply by 1 plus 1 on k plus 1, which would be the final term, the k plus 1th term, right? And we actually know, because we're assuming that this is true, this line here is true, we can substitute this first part here with k plus 1. And so what we'll get is this. Again, this first term, this first part here of the product is just simplifies to k plus 1, assuming this is true, and then multiply k plus 1 by 1 gives you k plus 1, and then multiply k plus 1 by this fraction just gives you 1. So this whole thing simplifies to k plus 1 plus 1. Which is actually really neat because we can look at the right-hand side and we can see that is actually what the right-hand side equals, right? The right-hand side is k plus 1 plus 1. So we have shown that p plus k plus 1 is true. P of k plus 1 is true. Okay, and so what we can do now is just to finish off our proof is conclude that well, actually, so let's say first that P of k plus 1 is true, and hence we've shown that P of k implies P of k plus 1 for any natural number k. And then so we can say by the principle of mathematical induction, it is shown that the P of n is true for any natural number n. And that's sort of how we conclude our proof. Hopefully you found that useful. Again, very fascinating idea, I think. Proof by induction. Still feels quite mystical to me, but hopefully making sense to you in terms of the process you need to follow and how you can use it to solve some interesting problems. So good luck with all your work, and I'll see you soon.